All right, everyone. Welcome to ASRG World Webinars, bringing you the latest in automotive research, innovation, and education. My name is John Heldreth, founder of Automotive Security Research Group, and we have a really cool presentation for you tonight. First of all, before we go into the presentation, let me quickly introduce myself. As I said, my name is John Heldreth. I'm the founder of Automotive Security Research Group, or ASRG. I have worked in the automotive industry for the last 15 years or so, and now focus my time on product or vehicle security. I'm originally from Detroit, Michigan. Shout out to the 313 in the US, but today I'm living in Germany and working at Porsche Engineering. Please feel free to follow me on LinkedIn or other social media platforms. I'm always happy to meet new people. So just quickly, the Automotive Security Research Group is a nonprofit company focusing on the advancement of the automotive security industry. It's a community to support the coming together of two areas of competencies, the IT security market and the automotive market. This is a community for you, for the automotive engineer, for the IT security specialist, for the beginner, for the experts, for the hobbyist, even for the people that are probably in the wrong YouTube channel. This is a community of volunteers. Our entire organization is built on the volunteer efforts of the administrative team and, of course, yourself. We're trying to remove the boundaries that can occur in the automotive security industry. This could be communication, borders, finding ways to learn different solutions, making good decisions, because at the end of the day, we all have the same goals: to keep our customers, to keep our friends and our families' data safe and secure, which can only be achieved together. If you want to get more involved, make an impact on the industry, start your own ASRG location, maybe participate in a technical committee or be part of a project, just please reach out to us. You can find out more about ASRG at www.asrg.io or send us an email at hello@asrg.io. So, before we go into the presentation, I'd like to show the overview of what's going on. If you see here, we have many new locations going on. It looks like something's happened with my font size for some reason. But today we actually have more than 5,100 members. We're in 31 locations worldwide across 16 different countries. But anyways, there's always the opportunity to bring ASRG to your home city. And so if you want to get more involved, if you want to be a lead of ASRG or start a network, start a community where you think people might have an interest, please let us know. And you could contact us at help@asrg.io. We have some really cool presentations coming up in the next few weeks. October 22nd, we have APMA IAC, Securing the Complete Mobility Ecosystem. And Colin and AJ Khan are going to talk about securing not only the product itself, but also securing the environment around it, and also in securing maybe the supplier chain. So really cool talk coming up there. We also have October 29th, 2020, Putting the Brakes on Cybersecurity Attacks, Targeting Connected Cars. Ken Monroe, he's an expert in the field. He's going to be giving us a little introduction about how to mitigate some of these attacks. He's working with penetration test partners, or pen test partners, sorry. November 5th, 2020. I can't tell you the title yet. It's still in the works, but Moabi is going to be with us. They've developed a software. It's a reverse engineering program, and really cool stuff here that's being generated by Moabi in the field of software reverse engineering, software quality, and the security of our coding. So really cool stuff here. November 12th, 2020, we have Anna Stilanio from SBD. The title is still open, but she's going to be giving us a talk as well. Really cool. Be there. You'll see all the stuff on YouTube. It will be live as well as available later as well. If you would like to give a presentation, please feel free to reach out to us. We have a dedicated email address for that. It's cfp@asrg.io. We have a lot of presentations coming up. We're so excited. We're so happy that the community itself is saying, hey, listen, I want to come present at ASRG. So if you do have a topic, if you do have an idea of something that could be presented, please feel free to reach out to us. We love, it's the community that supports the community. All right, so without further ado, we have a great presentation for you today. The title is LibreCAN, Automated CAN Message Translator. And Mert Pesé from University of Michigan, he's going to be talking to us a little bit about what this means and what it can do, and well, maybe what it can't do as well. But I'll let him clarify all of that stuff for you. Mert, thank you very much for being here.
Hello, everyone. Thank you for joining the YouTube live broadcast or tuning in later to rewatch this on YouTube. My name is Mert Pesé, and I'm going to be the presenter today. I'm going to present you as John said, my recent work, LibreCAN, Automated CAN Message Translator. So first of all, I want to thank all people at ASRG for giving me the opportunity here to talk and present my work. I want to start with some information about myself. So I am currently at the University of Michigan. I am originally from Germany, as you can see in that beautiful picture there. I'm from Bavaria, and I went to college at the Technical University of Munich, where I got my bachelor degrees and my master's degree, respectively. Currently, I am a Ph.D. candidate at the University of Michigan in the real-time computing lab of the Computer Science and Engineering department, and my focus is automotive cybersecurity and privacy. And even before starting my PhD journey, I've been proactive in this area, in the automotive security area, and I've been in this area now for pretty much 5 years exactly. All right, without further ado, let's get started. Let's get started with a really quick historical, with a really quick historical overview. So cars have been around since the late 19th century. The Germans invented it with the gasoline engine and the diesel engine in the late 19th century. And cars have been pretty much stagnant since then. There was, of course, always new developments, like cars got bigger, they got more powerful engines, but nothing really changed fundamentally until the 1980s, like 100 years later. This was when cars that were purely mechanical started to get more and more electronics in the car. And in the 80s, a protocol called the CAN bus, Controller Area Network, that we're going to talk about later in detail, was developed by Bosch, by Robert Bosch in Germany, again. And with the CAN bus and with more and more electronics in the cars, there was more functions that could be done in software. In the 90s, very popular was things like chip tuning or reflashing ECUs, modding the cars to get more performance out of the car. So a huge tuning scene developed in the 90s, in the late 90s. The 2000s were basically the time when more and more electronics came into cars, like navigation systems. They were very popular, more and bigger screens inside the cars. And then in the 2010s, something happened. So with more connectivity in the car, and with connectivity, I mean wireless interfaces, such as Bluetooth interfaces in the car, or cellular interfaces like LTE or UMTS modems inside the car. With more and more electronics in the car, more connectivity, people started to look at security vulnerabilities after 2010. Because cars became like computers with more connectivity and more electronics and more digitalization in general. People started to look actually into security. You have more attack surfaces in the car, and basically automotive security started on the big scale in 2010. And the time after 2010 can be categorized into three groups, into three categories of attacks. So the first generation of security vulnerabilities or attacks was pretty much in the first 5 years, 2010 to 2015. These were mostly attacks that focus on physical interfaces in the car. So they were basically looking at, okay, I'm plugging in a device in my car, and then I'm going to make the car misbehave. But they could only target one specific vehicle at a time, since they had to use physical interfaces inside the car. The second generation of attacks, that was from around 2015 to 2020, this year, these were attacks that focused on using wireless interfaces. And this basically started in 2015 with a Jeep hack. I'm pretty sure a lot of you have heard about that, where researchers could compromise a vehicle and could actually remotely control the vehicle to a certain extent. And this became more and more popular in the last couple of years. And by using wireless interfaces, for example, exploiting vulnerabilities in the infotainment system or the telematic control unit, it was possible for the attackers to scale their attacks to a certain extent too, because they could target more vehicles. In the first generation attacks, as I've previously mentioned, you can only target one vehicle at a time. It's not very scalable. But with a second generation of attacks, you can scale it. So technically, I think in the Jeep hack paper, they mentioned that by exploiting I'm not 100% sure how it went down, but by using using the sprints, some vulnerability in sprint system, they could target basically all Jeep Cherokees with model year 2015 that were out there that were equipped with the sprint modem. So definitely more scalable. And finally, the third generation of attacks, this is starting now with the rise of Android Automotive especially. These kind of attacks will focus on app ecosystems on in-vehicle infotainment systems. So Android Automotive, as I've said, this is getting more and more popular. The first cars are coming out this year, next year. With Android Automotive, it's going to get more scalable through that, because third-party app developers can basically exploit the Android framework if they find vulnerabilities, and can target more and more cars through that. And it gets easier then, for example, using wireless interfaces, most of them also short range. All right, so with the further scalability, the risk and the damage potential also grows. And all these categories of attacks, from the first generation to the third generation, they actually have a lot in common. So here we see a picture from the year 2015. This was a big year for automotive security, as I've mentioned. This was also the year when the Jeep hack happened. You can see that in July, affected 1.4 million cars. In all these attacks, it doesn't matter if you attack the car over a physical interface or a wireless interface. The final component to actually damage the car or do visible damage to the car is CAN injection. the final step is if you want to make the car misbehave, for example, accelerate instead of brake the car, you need to inject some sort of CAN messages into the CAN bus. And so this is called CAN injection. We will talk about this actually on the next slide. So let's break down this word CAN injection. What does this mean? Because there's a lot to tell you about this. This is basically some background slides about CAN first. So let's start with looking into how the electronic architecture within vehicles look like. So the in-vehicle network architecture is depicted in this figure. It is at least there's multiple architectures available for vehicles, but this is the most common one. It's called central gateway architecture. So basically, we have a master in the middle. It's a central gateway, which bridges different buses with each other. For example, there's a powertrain CAN bus, and then there's a body CAN bus, and there's like also other protocols and CAN, of course, in the cars like FlexRay, MOS, and these days also Ethernet. All these orange nodes that you see called ECU are nothing else than microcontrollers, basically. ECU stands for electronic control unit. This is a little computer, a microcontroller that is there for a certain specific task. For example, the engine control unit is to do all the engine-related computations. And there's multiple CAN buses. Usually in this architecture, ECUs are grouped by functionality. So on the powertrain CAN, you will find mostly ECUs related to the powertrain, like transmission, engine. On the body CAN, you will find ECUs that are related to the devices that are inside the car, or the buttons that you can press inside the car, or doors, windshield wipers, trunk, all that stuff. Yeah, so maybe very quick about like how many ECUs are out there in a car. So that heavily depends on the vehicle. It also depends on the vehicle how many buses you have. In some vehicles, you only have one bus. Most vehicles have like 3 buses. We'll talk about that later when I show you the experimental evaluation that we conducted on 4 vehicles, how the architecture looked on there. But as I've said, it heavily depends. It started out with 1 or 2 ECUs in the 90s, and I've read it. I read an article that in 2015, the average European vehicle had like 40 ECUs. Now there's premium vehicles out there with more than 100 ECUs. So the number of ECUs, at least in the central gateway architecture, is rising. Yeah, and as I've said, there's multiple buses in the car. There's FlexRay, there's CAN, there's MOS, there's LIN. We're going to focus on CAN because CAN is actually the most prominent and the de facto standard. So a lot of vehicles do not even have FlexRay buses or MOS buses anymore. They just have CAN buses because CAN has been out for the longest, and it's a very robust bus and very popular. So CAN stands for Controller Area Network. This is how a CAN frame looks like. So you have some header information here. Then you have up to 8 bytes of payload. You can put up to 8 bytes of data in there. And then you have a trailer. We're not going to go too much into like the frame format because it's not relevant for this talk. The important ones are actually the CAN ID that you can see here, the green box, which is the message identifier, and the payload field, the data payload field. So CAN is a broadcast protocol. So let's assume we have ECU A, which wants to send some information to ECU B. For example, ECU A sends some values, senses some values, and it wants to send it to the actuator that's connected to ECU B. So it's unlike an Ethernet, like in socket-based protocols, you don't have like a sender and a receiver in CAN, as you can see. The only thing that you have actually in the frame is this message identifier that's up to 11 bits long called CAN ID. The reason for that is because CAN is a broadcast bus. So what happens is ECU A sends out this frame. The CAN ID basically specifies that the message is from him and does this contain information that is coming from him. And ECUB will hear all messages that are on the bus, independent of if it's interested in listening to them or not. But if ECUB is interested in the specific CAN ID that ECUA broadcasts on the bus, then ECUB will set in its receive filter that, oh, okay, I'm interested. Let me take this message and process the data and look at the data, what ECUA wants to tell me. So this is how it works. In terms of security, CAN bus does not support any encryption or authentication. So let's focus on the first word, encryption. That means that the entire frame is unencrypted. The data is not encrypted. It's in plain text. Anyone who taps into the CAN bus, either physically or through the OBD2 port, we'll talk about that in a little bit, can read the entire communication on the bus and log it. The second part is that CAN bus does not support authentication. So anyone who is, again, on the CAN bus, who taps into the CAN bus, can send out messages, can broadcast messages. Yeah, so these are two big problems that CAN bus has. And the reason for this is because CAN, as I've said in the motivational slide, in the first slide, the CAN bus has been developed in the 80s. And there were only like 1 or 2 ECUs for the next decade. So nobody really thought that anyone would hack cars back then. And it's been out for like 30, 40 years now, and it's still in use because it's so robust, it's so good, and it works. There's why change a running system? So it was not developed with security in mind. That's a quintessence of it. Now let's continue with the second word, injection. What does injection mean? Like, what do I inject on the CAN bus? So the objective, why I want to inject a CAN message onto the CAN bus, is because I'm a bad guy. I'm a hacker, and I want to take control of the car, for example. I want to ditch the car I want to steer the car into a ditch. And in order to do this, I need to inject a well-formed CAN message to the IVN. IVN stands for in-vehicle network. So I can't just make up a CAN ID and a payload and broadcast it on the CAN bus. I mean, I can, but most of the time, nothing's going to happen. In order to actually do something visible, like a visible damage to the car or a visible action, I need to inject a well-formed CAN message to the in-vehicle network. And what is the challenge here? Well, the problem is, in order to inject a well-formed CAN message, I need to know the format, so I know actually what to inject exactly. Like, I want to know what causes the sudden acceleration of the vehicle. And this is a little bit hard. This is the main challenge that we're going to solve with this in this talk. The semantics or the translation tables are proprietary to the OEM. So let's look a little bit into this. How is data encoded? So here we see this is a certain CAN ID, let's say 123. And as I've said, the payload of a CAN message can have up to 8 bytes of data. So we see here 64 bits. And the colored boxes are signals. They're so-called CAN signals. So a CAN message can contain multiple information in it, multiple CAN signals. For example, the first 2 bytes of this specific CAN message can be the values indicating the speed of the car. And the golden ones can be a signal indicating the RPM, the engine speed of the vehicle. And there can be also areas in that CAN message, like byte 2 and the first part of byte 3, that are unused. There's no data encoded in there. And this information, what CAN ID contains, what information is stored in translation tables. And the most common format are DBC files. This is a proprietary format by vector informatic, but it's like pretty much the de facto way of storing these translation tables. And they contain what information can be found in which CAN ID and what position inside that 64-bit payload. Besides that, they also contain a bunch of other information besides the signal location. They contain also the scale and the offset. And the reason why it has a scale and the offset is because of this equation here. So let's assume the first two bytes again, which encode the speed. So the value here will not be actually like the absolute value. So if I'm going 70 miles per hour, we won't see the value 70 here, at least most of the time. It is an encoded value here that you first have to multiply with a scale and an offset and add an offset to it in order to obtain the absolute value. So this is how it's usually done, and scale and the offset are further parameters that are stored in these DBC files. What it also contains is a communication matrix. So the transmitting and the receiving ECUs of a CAN message. So if we have the CAN message with the CAN ID 123, it also stores who's sending it, which ECU is sending it, and which ECU is receiving this message. It also contains information about the sending type of the message. Some CAN messages are periodic, so that means that every 50 milliseconds, for instance, the message is periodically broadcast. But then there's also CAN messages that only pop up on the broadcast from time to time when it's triggered by an event. For example, when I open the door, it's not going to pull the door. I mean, some vehicles might, but usually it won't pull the door every 50 milliseconds and broadcast this in order to keep the bus load down, but only when an event occurs. So this is another information that can be included into DBCs. Usually, per CAN bus or per bus in general, there's one DBC. So if you look at the DBC files of a car, you usually have multiple DBCs, one per bus. And this is something I briefly mentioned before. Modern vehicles, at least North American vehicles, European vehicles look a little bit different. They also tend to transition to different architectures. Modern vehicles, at least in North America, they have 1 to 2 high-speed CAN buses and 1 medium-speed CAN bus. And this is an example how a DBC file looks like. So this is nothing proprietary that I reverse engineered myself or got from somewhere. This is a Tesla CAN DBC. It's very generic. It's on GitHub. There is a repo called OpenDBC from Comma AI, who hosts partially reverse engineered DBC files. And this is the KVaser DBC tool. It's free to use, that I've used in order to open that file because it visualizes everything really nicely. So let me just walk you through here. So here you will see the amount of CAN messages that the vehicle has. I've selected now one CAN message, and when I do that, I can look actually at what signals are included in there. So this CAN message, which apparently is speed related or contains speed related information, has a CAN ID 760. It has 8 bytes of data, and these are the signals in there. And you can also see how it's formatted. And for example, the GPS vehicle speed signal is the 3rd and the 4th byte. That's a green one here. It basically says what is the start, how long is it. The factor is a scale that we talked about before, and then the offset. And it also includes values like what is the minimum value of the speed? It's 0. Makes sense. What's the maximum one that can be encoded? It's 256 kilometers per hour. There is also more information that can be technically included in the attributes, like if is it a periodic sending type, or is it if it is, what is the cycle type, or if it's an event triggered. Since this is not the official DBC, but people have manually reverse engineered it and put it together, they're not going to contain this information, or who is a transmitting node. This is information that's not very easy to do. and that's the reason it's not in here. So I just wanted to give you like a brief example about how a DBC file looks like and what information it contains. Yeah, so, and this leads us to what is wrong with DBC files. I mean, basically, if you have the DBC file, you know the format, you know if you know what you want to do, if you know you want to accelerate the car, you just gotta look where is the CAN message and where's the CAN signal that makes the car accelerate. And if you have the DBC file, you can figure this out. You have the scale and the offset, so you can basically form a well-crafted CAN message and inject it to the CAN bus. Again, the CAN bus has no means of authentication, so any unauthorized node, as long as you tap into the CAN bus, can be over the OBD2 port, or you can physically tap into the CAN bus. You can inject any data you want. So the reason for this, or the reason why something is wrong with DBC files is because OEMs try to keep it hidden. They try to keep it secret, and they say, okay, by keeping it obscure, by keeping the DBC files obscure, nobody's going to hack my car. Nobody can damage my car, really. So this is the current mentality of OEMs. Instead, a lot of security algorithms, security standards, security definitions, they rely on Kirchhoff's principle. And Mr. Kirchhoff said that even if the security of a procedure is exposed, it's still going to be secure. So for example, look at AES encryption, AES-128, for instance. The procedure is public. You can look up the algorithm. But if you encrypt a message with AES, it's going to be definitely encrypted. And it's really, really hard to brute force AES-128. It's not correct yet. So this is the current automotive standard, and this is the problem. By keeping DBCs secret, you're not going to prevent automotive attacks. So the solution for, the solution for getting these DBCs, now you want to get the DBCs because we know if we have the DBC files, we will be able to do a CAN injection. And this is, as I've said, the crucial and the final usually component of all the automotive attacks. So the solution is you can do a manual reverse engineering. I think a couple of weeks or 2 months ago, we had a gentleman talking about manual reverse engineering with socket CAN and a Raspberry Pi. And this is probably one of the tools he used. This is CAN Sniffer. It's part of the CAN utils package of the Linux distribution, Linux operating system, sorry. And basically, when you can run this, and it will highlight you the bytes or the bits that are going to change while the car is running or while the data is being collected. And you can sit down and spend vast amounts of time, depending on how much you want to reverse engineer, and do it yourself manually by triggering certain events and then looking, okay, what changed? I invite you to rewatch the ASRG webinar from him if you're interested in that. But you can also do it in an automated fashion. Like, why spend all the time to do it manually if you can do it in an automated fashion? So first one is very tedious, and that's the reason I thought, okay, let's do it with LibreCAN. And we'll see how long it takes and what kind of data we need to feed our system in the next couple slides. All right. So before we go into the overview of our system, let's look at what data is actually available in cars. So there's two basic categories of data. The first one is powertrain or kinematic related information, like any kind of data that is really describes the dynamics of the vehicle. Can be information from the engine control unit or transmission control unit. I summarize this as the powertrain control module here, like the pedal positions, the throttle position, the vehicle speed, coolant temperature, etc. Also ADAS related information. And then body related information, as I've previously said, anything which you can press, like all the buttons and all the buttons, everything that you literally can press inside the vehicle, also like the doors, etc. So this is all the data that's available in car, and we're actually gonna try to look at all of this data except this one. like camera, radar, and LiDAR data, they're actually not usually, the reason for this is because they're usually not on the CAN bus. These are present in modern vehicles, especially cameras, and usually use like LVDS or Ethernet for this because the bandwidth of the data is not possible with CAN, which can only transmit up to 1 megabit per second of data. So what data are we reverse engineering now? Exactly. It's very similar to the previous slide. So on the left-hand side, we can see the powertrain related information. All the sensors that you can see in light blue are information that is also available over the OBD2 protocol. I'm going to talk about that on the next slide, what the OBD2 protocol is. And the dark blue one here are sensors that you can collect from smartphones. IMU sensors that you can collect from smartphones. And on the body-related information, you can see all these things that we're going to collect. We're going to talk about that more in detail later. But let's go back to the powertrain-related information. So we have 24 signals that we're looking at in our work. And for the body-related one, we're looking at 53 events. You see less than 53 numbers here, 53 lines here. But for example, if you look at the doors, it can be like the passenger door open and a passenger door closed. So you already have 2 events for 1 door. And then you have 4 doors per car. So you have 8 events just for doors. So, and this is how we get 53 events in total. So, of course, the question is, why do we look at only this data? In order to understand that, especially like for the first part here, why we're using this data that I've said is also available over the OBD2 protocol, we have to really quickly understand how automotive data collection is done. So there is a thing called OBD2 port. I've mentioned it briefly. For CAN injection, for example, it's necessary that you can access the CAN bus over this OBD2 port. So this is a port that's mandated in all gasoline vehicles after 96 in the United States. So all newer vehicles will definitely have it, if they're not electric. Of course, diesel vehicles have that too. It's usually located below the steering wheel. And it's standardized. And what it does is different things that we will see in a bit. But it communicates with the vehicle's internal network, with the in-vehicle network. So this is your access point to the CAN bus of the vehicle. If you don't want to tear apart your car in order to find the CAN wires to tap in, you can just plug in a device there and you have access to the CAN bus, or at least some part of the CAN bus. Then there's the OBD2 protocol. Don't confuse it with the OBD2 port. The port is just the connector, the interface. And the protocol, it's standardized in SAE J1979, is used for 2 reasons. So it's, first of all, it's used as a diagnostic protocol for mechanics to determine diagnostic trouble codes. So, you know, the check engine light that you see on your dashboard lighting up from time to time, that's what it does. The other thing is it is a higher layer protocol. It defines a higher layer protocol that returns absolute values of specific sensor data like speeds and engine RPM, the battery voltage, etc. These are like standardized so-called PIDs, parameters, and they're all some sort of emission related. That's the entire reason why they developed the OBD2 standard, because they wanted to have like a standardized way how to test emissions on every vehicle. And so like some of the data like speed and engine RPM or acceleration information even is already available to read from the vehicle. But the reason why we want to still reverse engineer the exact location on the CAN bus is because you cannot write anything to the CAN bus using this OBD2 protocol. If you want to write something to the CAN bus, you need to know exactly which CAN ID, what's the signal location. You need to know the scale and the offset so you can actually inject a well-formed message to the CAN bus. And the OBD2 protocol is only like for reading information about it. The tools that you can use, so I've said you can plug in a device with this OBD2 port. There's a bunch of devices out there. in our work, we're going to use 2 devices. Technically, you could all do it with the blue dongle, this ELM327, but it's cheap and the bandwidth is not good enough for reading CAN messages. So for CAN messages, you can use an OpenXC dongle. It's an open source dongle, I think, as well. It's from Ford. And you can flash different firmwares on it, different configurations on it, and filter out messages that you're not interested in. And you can log data with this tool. It's very powerful, and it's really, really good in my opinion. The second tool is the ELM327. You can get it for a couple bucks on Amazon. It's actually designed for talking the OBD2 protocol. It can, of course, also read CAN messages if you configure it, but again, the bandwidth is not great. So the ELM327 is there for speaking this higher layer protocol. You can also like get the DTCs of your car, like diagnose why the check engine light is on. But in order to use both of these devices at the same time, we need to use a splitter cable. It's called Y cable that you can see here, because you only have one OBD2 port. All right, so let's come back to the data that we're reverse engineering. This is exactly why we have this powertrain related information. This light blue part of the powertrain related information. This is actually information that is available over this OBD2 protocol, because we're going to use the OBD2 protocol as a side channel to locate these information within the CAN bus. Because if we have that, we actually know where to inject it. And we also like leverage the phone, like side channels, like sensors from the phone, in order to find more information, for example, about the GPS coordinates there. What CAN ID contains the GPS coordinates of the vehicle, or acceleration of the vehicle, etc. This is the first part. And for the body-related information, how we're going to proceed here is, well, we're going to use CAN sniffer again, for example, and log the data. And then we're going to apply some smart CAN filtering in order to reduce all these locked CAN IDs down to a much smaller set of candidate CAN IDs where the specific event will be. So for example, if we open our door, we will get, in the end, after a couple seconds of processing, we will get a candidate set of 5, 6 CAN IDs where this information can possibly be. All right, so how are we doing it? Now, this is the system design. We have 3 phases. The phase 1 will reverse engineer powertrain related information, whereas phase 2 will reverse engineer body related information. So let's start with phase 0. So our inputs to this system is the raw CAN data R. So we use the OpenXC dongle to record raw CAN data. We also use the blue dongle to collect OBD2 data. And we use the smartphone to collect IMU data. And phase 0 does basically 2 jobs. It does some signal extraction. So if you look again at this figure here, as I've previously mentioned, a CAN message can contain multiple signals. And we need to, before we start reverse engineering and mapping values to like the signal regions, we need to first identify the boundaries of the signals within that CAN message, within that CAN ID. So this is what signal extraction will do. There's different signal types that are usually available in cars. There's counters, check codes, and of course physical values. That's actually like the most important thing. And among physical values, there's physical values that might be unused all the time, that might be constant all the time, that might be multi-values. So multi-value is basically it's like an enum. You can imagine like 3 or 4 states that signal can be assigned at any time. A Boolean would also be a multi-value of 2, right? It's either 0 or 1. And this is actually very prominent, especially like with doors. Is a door locked or not? 0 or 1. And of course, others like real physical values. And this will have 4 stages, this phase 0, and we'll talk about that in the next slide. And we have 4 design parameters that we have in this, that we introduce in this phase, and we are going to tune these 4 design parameters in order to get the best performance in the end. And the second part is what phase 0 does is the alignment. So because we're using the smartphone in the car in order to use this as a side channel for IMU sensors, we need to make sure that the coordinate systems of the vehicle and the smartphone are aligned. And this is something that we also do in phase 0. So I'm going to talk about the signal extraction process because this is one of the most complex parts of this work. And so as Seth previously said, it has 4 stages, consists of 4 stages. Technically 5 if you include the pre-process one too. So while I'm going to go through this, I'm going to refer to this little figure up here, to this CAN dump that I have here. So only look at lines 1 to 4 of CAN bus 0. Well, I'm just going to talk about it. So we first start by splitting the trace. So the entire trace, we see 2 CAN IDs, 1, 2, 3, and 4, 5, 6. So basically what we do when we split the trace is we group by CAN ID. So we're going to take the huge log, which can be like multiple megabytes long if you collect long enough, and we're going to write it out to like 2 separate files, 1, 2, 3, and 4, 5, 6, because we're going to like inspect every CAN ID sequentially. Then in the pre-process stage, now let's say we're only focusing on 1, 2, 3. So look at lines 1, 2, 3, and 4 here, please. We're going to calculate the bit flip rate for each of the 64 payload bits. So for example, if you look at the first byte here, it's 21, and then the next timestamp, it's going to be 22. So each two, this is in hexadecimal, by the way, so each 2 numbers will represent 1 byte. So the first 4 bits won't change at all from 21 to 22. But here, in the last 4 bits, 1 bit will actually change because it's going from 1 to 2. And we'll do this over the entire length of the trace. So for example, in the next instance, we have 23 and 24. So we're going to basically increment a counter of how much every bit changed over the time, and then divide it over the amount of lines. So in this case, it would be 4 lines. And we're going to store this in an array for each of the 64 payload bits. So this is, we call it the bit flip rate. We're going to refer to it as BFR and the following. So in stage 0, this is this stage. This is actually also like the first stage where we're going to have a design parameter. This is where we will generate preliminary signal boundaries. So we will start segmenting the 8-byte payload into different signals, but these are not going to be final. So this is like the first step. And we will label the different signals that we find as unused, constant, or possible. So basically what we're doing here is we're looking at the bit flip rate that we calculated in the previous stage, and we're going to identify regions that that change or that do not change at all. There's a lot of like signals that are unused, for example, because there is no signal defined there in the DBC, or there is constant ones, basically all ones, or one and a lot of zeros, like signals that never change. This is also something possible. Imagine, for example, the airbag, right? It is a signal that's physically present, but in most cases, you're not going to trigger the airbag unless you crash your car. So this is something that you won't be able to trigger in regular recordings. And so areas that do not change are either unused or constant. And in order to fine-tune this, we have 2 parameters here that I'm not going to go too much into detail. I will, in the end, refer to the paper to where you can actually look what it is. But it is for tuning the boundaries. And the second big category is possible. This is basically areas or regions inside that payload that change. And this is, in the next stages, we're going to break down POS further into the different signal types. So in stage 1, we're going to look at the signals that we label as POS, as possible, and that we're going from left to right. and we're looking at the bit flip rates. And if we see that the bit flip rate of the next bit it decreases more than a certain percentage that's defined by the parameter TP02, then we can say, okay, this is probably where the signal must end. And the idea behind this is, if you especially look at counters or also like physical values like speed that are represented in binary, the least significant bits are going to flip more often than the most significant bits. Like for example, if you go from if you go from like 21 to 24, the most significant bits are not going to change at all, but it's going to like be the least significant 3 or 4 bits that are going to flip a lot. And this is just how binary works, and we're going to leverage this knowledge in order to finalize our signal boundaries if the bit flip rate of the next bit that we're looking at is decreases larger than this percentage defined in TP02. Then in stage 2, so by stage 1 we will have now all our signal boundaries finalized, but right now in terms of labels we only know the unused ones, the constant ones, and possible other ones. Pos is basically everything else in unused or constant. It can be a regular physical value, it can be a counter, it can be a multi-value. So in stage 2, we're actually determining the multi-values by using the design parameter TP03. And in stage 3, finally, we determine counters, because counters have a very easy pattern to follow because they increment by 1 at each occurrence. So that's very, very easy to determine at the end. Right. So that's how phase 0 works in a nutshell. It builds on top of read. So stages 1 and 3 are partially done in read. Later on, when I'm done with the presentation, I will also show you the reference slides where you can read the original paper of read for that. But everything else it has been designed by us. So now we have the signals extracted, the coordinate systems aligned, and now we can actually start reverse engineering powertrain related information in phase 1. So our inputs here are the raw signals, small r, and then our side channel informations, D and D prime, which are the OBD2 signals that we got with the blue dongle, and the IMU sensors, D prime. And so what we first do is we take the CAN signals, like all the CAN signals that we could extract from the entire log, and we take the side channel signals from the OBD2 dongle, the blue dongle, or the phone, and we resample it to the same length. That's very important because usually, like the OBD2 protocol samples like all the data at 10 hertz, I think, and you want to make sure that everything is resampled to the same length. And this is a knowledge that we've previously discussed. There's a linear mapping, a linear encoding between like the CAN value in the payload and the absolute value that is determined by the scale and the offset. And basically, by using this equation, we can kind of like predict the next step. The CAN value is the one, what we get from the CAN signals R, and the absolute value is the one that we can get from the side channels D. So we do not know the scale and the offset, but we know there must be like super highly correlated because of this linear relationship. And that's the reason we use normalized cross correlation between R and D. And we run it like literally for each side channel. I think we have 24 in total. We run for each of these side channels, for example, the engine RPM, we run it with all the possible signals, CAN signals that we extracted in phase 0. And then we rank them according to the correlation score. So the correlation score of 1 means they're perfectly correlated, and 0 means they're not correlated at all. And if we rank them, we see that for engine RPM is very, very likely, located in CAN ID 516 on CAN bus 1 within these signal boundaries. And we get a ranked list, but we do not actually know like which one is it now, because basically what we do here is we get a list by running it through the entire possibly extracted signals, and then we rank them. So we need to define a cutoff point where we're like, okay, so the first X of them are possible RPM values. So if you inject to 516 on CAN bus 1 or 1071 on CAN bus 2, etc., these ones are the ones where you will actually like be able to spoof the RPM. And this cutoff point is determined by a parameter TP1, and it's actually very, very simple if you look at the values in this example. If TP1 defines a percentage decrease from the value to the next value, and if it's larger than that, we'll define the cutoff point here. So the first ones have very, very similar correlation scores. They're all around 0.97. But then here, it suddenly jumps to 0.91. So that's a huge decrease. And TP1 defines how much this decrease is allowed to be. And once the threshold is surpassed, we're putting the cutoff point there. Okay, so now we have the CAN IDs and the signal location, like the signal position within that CAN ID. But we still need to figure out scale and the offset. So we actually, like, when we inject a value, we can like actually inject the value we want and not like a random value. And this is possible by, for these 4 candidates that we have here, to run linear regression. And since it's a linear relationship here, and then we can determine the scale and the offset. So in phase 2, this is the phase where we reverse engineer body-related information. We are going to look here what our input is. Our inputs is again the raw CAN data R. So we're not looking actually at the extracted signals from phase 0 right now. We don't really care about that. We're looking at the entire log. So phase 0 was more precursor for phase 1, but phase 2 can operate independently on the entire CAN log that has been recorded. And also like the events, the 53 events, for example, turn on your windshield wipers, close your door on the left back, etc. Yeah, so let's talk about the reference snippet, what that is. So the reference snippet is a specific event that we record besides the 53 events, where we make sure that nothing is really running. So this is like more or less the baseline. So accessory power is on the vehicle, because if you don't have any power on the vehicle, a lot of the ECUs are going to be in standby, or they're going to be sleeping, so you won't be able to see any of their CAN messages. So we need to make sure that the accessory power is on, but the engine is off. We also make sure that the AC is off, that not the radio, the infotainment unit is off, so nothing is really running. So this is like the minimum set of CAN messages that are in the car that we can record. This is called the reference snippet. So this is something we record, and then we record the 53 event snippets. And we wrote a companion app for that called Detroit. And I'm going to talk about Detroit at the end of my presentation a little bit. How we use this Android app to interact with the user, and the user, it will basically tell the user, for example, I want to record the event now on buckle driver. So you click on start when you do it, and then you unbuckle yourself, and then click next event, or stop when you're done. And this is how and it will automatically record the CAN logs and label them according to the specific event that you're doing at that point. Yeah, and so a brief example how this will work, because I've mentioned that phase 2 is doing smart CAN filtering on the raw CAN data. So let's look at the specific example and go through it. So phase 2 has 3 stages. In the first stage, we filter out constant messages. So these are messages like that never change over the time that the data has been collected. Right? So for example, CAN ID 300 stays the same for the entire CAN trace. It's constant message. It cannot be really related to any of the events that we're doing. If you're, for example, opening the door, we expect that this is visible in the CAN message, that some bits flip. But if it stays constant along the lifetime of the trace, then we can be sure that this is not related to that event that we just recorded. So we can kick out the ones with CAN ID 300. In the second stage, we do a diff with the reference snippet or reference state. and we basically filter those out. So if we find CAN IDs, like the blue ones here, CAN ID 600 and 400, that are in the reference state and do not change at all, then we can be sure this can't be it either, because these were like the same messages that were also like present in the vehicle while the car was running. So it can't be that. While the car was not running, sorry, while we were not doing anything. So this is something also that we can filter out. And finally, in stage 3, we're going to look at CAN IDs and filter those out that are related to powertrain messages. So this is where we're taking the input from phase 1, because in phase 1, we're identifying the CAN IDs of powertrain messages, and then we give this information to phase 2. And for example, message 500 and 700 have a very high correlation score from phase 1, so we know these are actually powertrain related. And we can filter those out too. So all the ones here that you see in color are going to be filtered out, and all the others are possible like candidate messages for that certain event that we're looking at right now. We have 2 parameters here. So I'm not going to go too much into detail. The first one is as a threshold parameter for creating the reference state. So when we do the diff in stage 2, we're not really doing the diff to the reference snippet, because in the reference snippet, you will still have like the CAN IDs that are going to change all the time. It's not like perfectly constant all the time. There's still like going to be some CAN IDs that are going to change. So you need to create a reference state, and this algorithm is also described in the paper that I'm going to show you at the end of the presentation. And the second parameter is actually like the minimum correlation threshold that defines what is considered a powertrain related CAN ID, right? So for example, if you look here, in our example, I think we set it to 0.8. So everything, well, for all the CAN IDs that we have here that are above 0.8, we say that these are powertrain related and we can filter them out. And also these 2 parameters are going to be tuned in order to get the best performance later. All right, so experimental setup, like this is basically the system design, phase 0, phase 1, and phase 2. And yeah, we came up with this, and we also wanted to test how good it is. We wanted to find what are the best parameters, and by using the best parameters in each phase, what's going to be the performance? How good is LibreCAN? And we used 4 different cars. They're all from the same OEM. Can't disclose the name of the OEM because of an NDA. But we had different kinds of vehicles. So vehicle A was a sedan, vehicle B was a small compact, vehicle C was a mid-size compact, or like not a mid-size compact, a mid-size SUV. Vehicle D was a pickup truck. So different kinds of vehicles. They were all newer than 2016. So all newer vehicles. And the reason I'm not naming the OEM's name is because we had a NDA with them, and they gave us DBC files. So we had a ground truth to actually check our generated DBC to the ground truth, the original DBC that they provided us, so we could assess actually the performance of LibreCAN. So for the raw CAN data, as I've said, I've used the OpenXC dongle because it's pretty good, and it has a companion app on Android called OpenXC Enabler 2, which is responsible for interfacing that dongle and logging the information. And for logging the OBD2 parameters, we use the Elm dongle, the Elm 327 dongle, this blue dongle that I've previously mentioned, with the Torque Pro companion app on Android. So let's start with evaluating performance of phase 0. So phase 0 was the signal extraction phase. I said we had 4 parameters that were used in different stages along phase 0. And we want to optimize now the combination of these 4 parameters so we can maximize the number of correctly extracted signals. So here in this table, we'll see in the first column the correctly extracted signals. So how many of the signals that we extract are actually correct according to the ground truth DBC that we have. The second column is the number of total extracted signals. So how many were we able to extract in total from the vehicle? The third column is taken from the ground truth DBC file from the OEM's DBC. This is the number of total signals that is available within each vehicle. And then we have two ratios. So let's start looking at this ratio, the total extracted signals over the total signals that are available in the original DBC. And we can see that we always have about 50%. So more than half of the old signals can be reverse engineered. This is more like a coverage metric. How much of the original DBC can we reverse engineer? And it is more than 50%, yes. And this might look low, but I want you to consider that a lot of the events or a lot of the signals can never be triggered, really. For instance, we didn't deploy the airbags, right? Or we've never sent an emergency call. So there's certain events that is very, very hard to trigger. Also, in the original DBC, there's like signals that are related to AUTOSAR network management that we cannot really reverse engineer because there is no corresponding powertrain related or body related event that we can leverage in order to reverse engineer that. So this number might look low, but it doesn't really say that much. The second number is the ratio of correctly extracted signals to the total extracted signals. So it basically says, so we extract, for example, for vehicle A, we extract 846 signals in total, and only 308 are exactly correct. Like they match exactly the signal boundaries that are specified in the DBC. And we see that the performance here is around 30%. So matching the exact signal boundaries is difficult. And again, this is not a huge problem actually, because imagine the speed is 2 bytes long, 16 bits, right? And the maximum is 250 kilometers per hour. Here in Michigan, at least where we are, we're not allowed to drive that fast. The limit is like 120 kilometers per hour, I think. So we're never able to trigger the most significant bits of a signal, especially like of the powertrain related ones, right? And this is the reason why we can never match the exact signal boundaries, just because we cannot push the vehicle to the maximum possible value. Also, we're not going to drive 8,000 RPM. That's another example. Right. So, but we will see, although these numbers might not look like super promising, it doesn't matter because out of the signals that we actually reverse engineer, we're going to get pretty good performance. So let's look at the powertrain related signals first in phase one. So we have a confusion matrix in order to, because it's basically a binary classification thing, what we're doing here. And we set up a confusion matrix. So let me just go over this table really quickly. So here, the result from phase one basically means like, what did we assign to engine RPM, for example, which CAN IDs and which signal locations that we assign to engine RPM, or which ones did we assign to speed. This is our output. And the ground truth is the original DBC from the OEM for engine RPM, which are the specific CAN IDs that are actually representing the engine RPM. And then we can basically define true positives, false negatives, and true negatives. And we can define two metrics, precision and recall. So precision is the ratio of true positives to the sum of true positives and false positives. So if you go here, true positives are the signals that are correctly identified as part of the ground truth. So the higher the true positives, the better for us. And false positives are the signals that are incorrectly identified and are not part of the ground truth. So a high precision would mean low false positives. So it would mean among the signals that we identify for vehicle speed, for example, a high precision would mean like most of them are actually correct. There's only like very, very little of them that are faulty, that are actually not related to vehicle speed in this case. The recall is a ratio between true positives and a sum of true positives and false negatives. So false negatives are the signals that are not identified but are part of the ground truth. So a high recall would mean a low number of false negatives. And these are basically these are basically sorry, that are defined in a ground truth, that that we look in the DBC and can see for vehicle speed there's this and this CAN ID, but that we are not able to really find using the phase 1 of LibreCAN. And usually when you have like a binary classification task and a confusion matrix like that, you do a ROC curve, a receiver operating characteristic curve, in order to find the best performance. Since we have an imbalanced data set, we are using a thing called PR curve, precision recall curve, that's here. So we can see different colors. Each color stands for one of the vehicles. We see for each of the parameters, for each parameter in phase 1, like TP1, we had only one design parameter in phase 1. We basically calculate the precision. We let phase 1 run for each parameter, and then we calculate the precision and the recall and plot it here. We want, in general, high precision and high recall. So the closer the values are to this right top corner, the better for us. And yeah, we're just going to choose now the optimal design parameter is the 1 point, which the Euclidean distance from that point to this right top corner is the smallest. That's how we define the top point, and that's how it's usually done. And for our top parameter, for our most optimal TP1, we get these numbers. So we can see that we have a precision hovering at around 80%. So that means basically among the signals that we identified, among the list that we return, 4 out of 5 on average are actually correct. Most of the identified signals are actually correct. So that's what it means, which is good. So in phase 2, we do the same thing again. We have another confusion matrix. The interpretation of that is, of course, a little bit different here than phase 1. And we can also, again, define metrics like precision and recall, but we can also look at accuracy. So accuracy uses pretty much all of these four quadrants, including the true negatives. So true negatives are very important to understand phase 2. True negatives mean basically the CAN IDs that were correctly identified as not being related to an event. And this is what we want. We want actually a high number of true negatives because, and you can see it here in this figure. Let me just show you this figure. We start with, for example, 100 CAN messages with a total of 100 different CAN IDs. The blue ones, by the way, mark vehicle A, and different colors represent different vehicles. But let's just look at vehicle A. So we start with over 100 different CAN IDs in the log, in the CAN log for vehicle A, and then each of these ticks on the x-axis is one of the filtering stages. And in the end, we can see, it's decreasing, which is good. And in the end, we can see that we have around 10, 12 CAN IDs remaining. So we eliminated 85, almost 85 CAN IDs over the entire filtering stage. And if most of them are actually correct, like out of these 85 that we eliminate, that they're not related to this event, then the true negatives are going to be very, very high. And that's the reason I think accuracy is the best metric in order to characterize phase 2. And we can see that our accuracy is usually over 90%. It's very, very high. And that's literally what you can see in this picture. We reduce the number of CAN IDs by more than 10 times on average, which is very good. So you're still going to have, like, for example, 10 CAN IDs, and maybe only 1 or 2 CAN IDs are actually really related to this event, and 8 are not, right? But you can do a manual inspection, and with a manual inspection, like, further reduce down the 10 CAN IDs that you have in the end, instead of like going through the entire 100 CAN IDs, right? And that's the reason the precision is actually low. It's around 10%. So assuming we have 10 CAN IDs left at the end, and actually only 1 CAN ID is really related to this event, 9 are going to be wrong. 9 are going to be CAN IDs that we said, okay, these are candidates, but we're not sure about it. And this is exactly what the precision says. So it's actually in accordance with the results here. And we're not saying we want a fine-grained, or we're going to provide a fine-grained a reverse engineering of body signals where we identify exactly the one CAN ID and exactly the signal location within it. We just reduce the number of all the CAN IDs by a factor of 10. So by manual inspection later, you can narrow it down even more. And this is an example for the pickup truck, I think, for all of these events. The blue one is the raw event, like the number of CAN IDs that we can record during this event, and then it goes down for each event, as you can see. So interesting that for certain events you can record actually more CAN IDs than for others, but they're usually between 100 and 120. All right, a couple more metrics that we want to look at. So we mostly looked at the performance so far. The coverage, how is our signal extraction going, and then how accurate or how good is our reverse engineering of powertrain related information. We saw that the precision is usually around 80%. And then the body related information, we saw that the accuracy is around 90%, mostly over 90%. And then we can filter out the CAN IDs or reduce the number of CAN IDs by more than factor 10. We also wanted to see how to apply it generically. So this is the problem here. We have all these design parameters from phase 0, 1, and 2, and there's a certain range. The range is usually given by a logical thing, and 0 to 64 because there's only 64 bits. We need to look up the exact definition of what TP00 means in order to understand these ranges. But what we're basically doing in all this extensive testing and these PR curves and everything that I showed you is we are brute forcing this entire range with a certain step size that makes sense. And then we're trying to get like the best parameters in order to get the best precision, the best recall, the best accuracy, right? And for each vehicle, these optimal parameters are going to be a little different. But here's the thing: we can do this. We can do this because we have the ground truth. We know what is going to be the best, and we can fine tune our parameters according to that. But in real world testing, you don't have the ground truth. I mean, this is what you want to get, what you want to obtain. That's the reason we have to propose a generic set of parameters that can work with pretty much any vehicle. And we use 4 different vehicles that are of different model types, everything, even different model years. And we saw that a lot of the parameters are actually very, very close to each other. So the choice of the parameter does not depend really that much on what vehicle you're using. And anyway, we're suggesting a generic set of parameters that you can use that works. They should be working fine with any vehicle. This is what happens here if you run it with these generic parameters instead of the most optimal parameters for each vehicle. For phase 2, actually, nothing's going to really change. It's pretty much the same. So the orange ones are the ones with the generic values, and the black ones are the ones with the optimal ones for each respective vehicle. And you can see that the numbers are actually like decreasing maybe a little bit in terms of precision. For vehicle C, actually, it's going up. But especially in phase 2, nothing's really changing. So the performance metrics barely change, and this is why we can say that generic configuration can be used for any vehicle. So if you guys want to use LibreCAN and have the code for it, or want to re-implement LibreCAN and want to know what parameters to use to get an optimal performance, you can just use this generic set of parameters here. We also looked at some other metrics, like manual effort. I mean, we said it's an automated framework, yes, but we need to feed the system some data, right? And we need to, of course, collect data to feed the system. So all of our traces that we collected for each vehicle was 1 hour long. We also looked actually at the precision for phase 1 in terms of using only 30 minutes instead of 60 minutes, 50% of the trace and 25% of the trace. And we saw that actually for 50%, it's still sort of acceptable. So 30 minutes of free driving data is sufficient, but the more the better. Using 1 hour is better. It will yield you better results. If we can collect more than 1 hour, even better. But 30 minutes is the absolute minimum you should collect data. And this can be data that you can collect while you're driving to work on your commute. There's nothing you have to really do. You just have to kick off like plug in a dongle, start a collection on the companion app, and that's it. And when you're done, click stop, and then you will have the log, and you can feed it into LibreCAN. And phase 2, for recording the phase 2 events, the 53 events, like closing the door, opening the door, turning on the radio, turning on the AC in the car. This is actually time that you have to take and where you have to like record all these events. We provide a companion app for that, so you can really start and stop the recording for each event, and it will label it and everything. And we conducted a human study. I think we had 13 participants here, and some were familiar with the car that we use, some were not at all, some were novice drivers, and we just wanted to time how long it really takes them to use our Android companion app and record all these 53 events, like loop through the entire events. And on average, it took them 10 minutes. So it's actually not really a lot of time that you have to spend on there too. So in order to summarize, 30 minutes of free driving data and 10 minutes of experimental data for phase 2, so a total of 40 minutes, is sufficient data to feed into LibreCAN. Of course, the more data you feed in the free driving portion, the better is the performance. We also looked at how long LibreCAN takes actually to process the entire thing, to basically reverse engineer everything, to run through all 3 phases. We used a powerful Linux workstation, a headless workstation running Ubuntu 16.04. And for all the vehicles, we can see it takes less than 90 seconds. So it's actually pretty fast. And if you want to do it maybe like on a less powerful spec than this, which we probably all have on our laptops, it's still gonna take less than 5 minutes. So it's really fast. And most of the time is actually spent on phase 1. Phase 2 takes only a couple seconds, and phase 0 as well. So phase 1, I think, took like at least 60 seconds out of this time. But you can see like the breakdown in the paper as well. Yeah, this is a slide where I compare LibreCAN with work that has been done before. There's no solution that did all of these 3 phases, that reverse engineered body-related data, that reverse engineered kinematic-related data. There's no work that did it all. There is this one work called READ. By the way, the references, I have a references slide, so I can show you the 2 papers at the end, so you can have a look at that if you like. READ only does signal extraction. We actually built phase 0 on top of READ. And you're probably going to ask me, like, why is it lower than READ if you like build it on top and improved it? The reason was we used newer vehicles, more complex vehicles, a lot of signals in the DBC, and the guys from READ used a very old vehicle, not a very complex one with much smaller set of signals, and that's the reason they were able to identify more. They probably also cut down the DBC file to only the ones that can be technically reverse engineered, or where you can actually trigger when you collect the data. So that would explain it. But then compared to ACTT, which did some sort of phase 0 and phase 1, although not the same way we did, or not the same extent we did, we're definitely better than those guys. And phase 2 is completely novel. Nobody has looked at that before. Before I conclude this work, I want to talk about Detroit, an application of LibreCAN. So this was a framework that we developed and which contains LibreCAN in order to reverse engineer the messages. So Detroit is an open source framework. It's for vehicle agnostic data collection, translation, and sharing. So Detroit is actually an acronym which stands for this. And it's basically a tool which consists of different components. It has a backend, it has a front end, which interfaces with the vehicle, and a cloud for the developers. So it is a tool to collect data from any given vehicle, and given that the DBC is present, and the DBC, if it's not present, can be reverse engineered using the baked-in LibreCAN solution. So this is also a tool to crowdsource DBC files in automated fashion, it is possible to collect raw CAN data from the cars, and it will get translated since we have the DBC, and then you can share the translated values with third-party developers. Third-party developers have a web user interface, a developer portal where they can register their apps, and these will pop up on the phone. It's like an app store kind of thing, but you don't really download anything. You basically just enable and disable the data collection for certain apps. You will be shown what kind of data this third party wants, and the third party will then collect the data through the backend, and it will get translated, and then it will end up at the developer portal. By the way, this link is also going to be on the last slide on GitHub, is where you can download the Detroit framework. Yeah, this is basically the system design of Detroit in total. Interesting thing is there's two ways how to collect and share data. It can be like it can be offline or online. So that means for real-time applications, the data can be translated and can be streamed to the developer's backend to process in real time ASAP with only a couple of milliseconds of latency. Or you can collect the data, get it translated, and then you can download it in the developer portal if it's not a real-time application. And you can download it even in like MATLAB or NumPy format for further processing. So it's also a very valuable tool for academic researchers. But I'm sure that a lot of commercial, a lot of people in business and industry might want to use that, especially if they have startups and they really need some data and they want to have a look at data and collect data. This is a great tool. And you can write this down. It's also going to be like on the last slide. This is a Google form, Google survey link, where you can provide me your email address if you're interested in this, and give me like a brief purpose of why you want to use it. And I can share more specifics about this, and I can provide you the Android app that works with the backend that we're running. So you can actually test and use Detroit. All right, so this talk showed us LibreCAN, an automated CAN message translator. And from a security perspective, it showed us that the car hacking barrier can be very easily overcome by reverse engineering, especially if you do it in automated fashion. You don't have to spend months or days, depending on the scope of how much you want to reverse engineer, manual, tedious work anymore. You can do it with only 40 minutes of data collection, feed it into the system, and in a couple of minutes you have like a custom, like a generated DBC file, basically. So the automation aspect is great, and it's the first framework actually in the world that can automatically reverse engineer both powertrain and body-related information. The performance is pretty good, as we saw, like precision and accuracy numbers, especially compared to related approaches. And it's also very, very fast. We saw that at actually even less than 90 seconds on our powerful workstation. So it can be easily run on mobile workstations, on your laptops as well. And we also showed that the security by obscurity paradigm that OEMs follow, which is the current automotive standard by just not disclosing DBC files and hoping for the best and nobody's going to attack their cars, is outdated. And it has to be replaced by Kirchhoff's principle, which is our suggested automotive standard. OEMs should not be afraid of sharing their DBC files because cars will get hacked anyway. They need to look into different ways of protecting their cars, and they have to look into different countermeasures. Yeah, so this will conclude my presentation now on this. So before I say thank you, I want to thank the people I worked with during this project. We spent a good amount of time in implementing and testing this. So two of my students, Troy and Andres, who worked with me, a big thanks to them, because they spent a lot of time coding that entire thing up and making it very, very nice. Then also other lab mates of me, Ph.D. students, Eric and Doniel, who work with me. And finally, of course, my Ph.D. advisor, Professor Shin, without whose support this would not have been possible. Final thoughts, final things that I want to mention. This is my email address. You can see here. You can read the paper under my website here, under the publications tab. I have a PDF. I also have some slides. I have a trimmed down version of these slides available there too, if you want to like download the slides. And the last two links are about Detroit. So this is the link to download Detroit, or like download the source code of Detroit. We'll have two repositories, one backend repo called OpenIVN, and then there's one Android repo on this account that is basically the APK that you can build yourself. I want to note that the backend OpenIVN, where LibreCAN is featured, is not included. So this is stripped out because it's patented technology. But if you want to participate in using this, the backend is already running on our server. So if you want to participate, and this is the link here, the last link is the form in order to reach out. If you're interested, in contact me. If you want to like use this, I can provide you the APK, or you can compile it yourself if you want. But I mean, I can just give it to you, and then you can install it on your Android phones and connect to our backend and do all that stuff. I will also show you instructions how you can register for the developer portal if you want to register your own app. All right, so thank you very much for listening. And yeah, now I'm open for the Q&A session. If you're interested, some references here too of the two papers. I'll keep that on here for a minute.
All right, Mert, thank you so much for great overview and a great tool that you guys have developed there at University of Michigan. Is this your PhD work?
It is, yes, part of it.
Part of it. All right, very cool. It looks really interesting, and building these relationships between, looking for relationships in the values is always really interesting. We had two questions from the audience. The first one is from Raul. He's asking, is it possible for OEMs to prevent reverse engineering of the DBC files?
Well, there's only one way they can do it. They can encrypt the CAN bus. But CAN bus encryption will lead to more problems because you have resource-constrained devices. Like ECUs are resource-constrained. If you want to add encryption, you're going to, besides storing the keys and all of that, you're going to introduce a lot of latency. And if you introduce encryption and decryption latency to the entire process, you're not going to be able to meet the deadlines of certain safety critical messages. So that's why encryption is not something that really is feasible. But technically, that's the only way you can really like prevent that.
And what about with the new types of CAN, like CAN-FD, or the new types of CAN which allow for larger bit length and potentially also corruption, what's it called? Encryption.
Right. If it's still plain text, if it's not encrypted, just like a bigger payload, of course, there's more data. So the processing, you of course have to change LibreCAN to work with FD. So it would be LibreCAN FD. You have to like change a couple things, and it would probably take like a bit longer in terms of processing time because there's just more data to process.
Mm-hmm.
But if it's plain text, the idea of LibreCAN would still apply without any problem. So if you encrypt, and again, you can do it, especially with up to 64 bytes, if I'm not mistaken, in CAN-FD, you do actually have the chance to like also encrypt. That was actually another reason why CAN is not great for encryption. Like you cannot use AES-128 because of block sizes of 16 bytes and an 8-byte payload. But with CAN-FD you can. But again, even although you have faster data rates, you still have resource-constrained system, and if you want to encrypt CAN-FD, you're going to add latency. And I think this is more like a design choice for OEMs, but again, if it's encrypted, there's no way you can reverse engineer it.
Okay, great. Thanks for the answer. Another question coming from PP. I guess SecOC won't have an impact on reverse engineering, but surely it can prevent injection and spoofing signals, correct?
Yes, I mean the injection part is more because it's not because CAN bus does not have any means of authentication. Like any unauthorized device, for example, through the OBD2 port, can participate in the CAN broadcast. It can not only read, but it can also write to the CAN bus. But if you introduce authentication mechanisms where you can discard messages from CAN nodes that are, not part of the original CAN network, then you can definitely prevent that. But this is only for external attackers, like attackers that try to join the CAN bus by adding their malicious node to it through the OBD2 port or wherever. But if you compromise an ECU, like for example by exploiting its remote surfaces, like the infotainment unit or telematic control unit, whatever. But if you achieve to compromise it, then this won't really help because it's like a legit node that's sending it, right? So you can still do a CAN injection over there.
Mm-hmm. Okay. All right. And Mert, so what you guys have done with LibreCAN is something like the Comma AI project, isn't that correct? Or what's the difference? Maybe can you explain that to us?
The Comma AI project, and I've actually showed Tesla DBC as an example. And they actually host a bunch of different DBC files for different manufacturers, different OEMs on their GitHub repo. What they did, from my understanding, is that they actually manually reverse engineered them. And their scope was to reverse engineer as much as possible. I think Comma AI cares more about automated driving. So they were more interested in kinematic related information that they want to read. So they manually reverse engineered only like a subset of CAN signals that they were interested in. But this was not an automated process.
Yeah, what I saw was that they were actually using video feeds or something like that to determine whether the car was turning or moving forward.
Yeah.
And to look for those changing signals on the CAN bus.
Right. They were using ADAS systems like the camera as the side channel information, just like the way we use the OBD2 or the smartphone. I said, I personally think if you get your phone aligned with the car's coordinate system, it's much easier to use the gyroscope in order to detect turns and doing computer vision stuff on the camera. But they're using it as a side channel as well. And there is actually no reference that they are doing it in an automated fashion. I think what they did is they actually used this as a side channel, and then they manually inspected the CAN log, and they knew at what time there must be that change. So they actually did it by manual inspection, but they used the side channel of camera feed in order to narrow it down for themselves, to reduce the amount of manual work. But it's not automated the way we did it. This is literally totally automated. You throw in the data into LibreCAN, and then you have your DBC at the end.
Okay. And so is there any plans to extend or improve the kind of like algorithm that you guys are using? I mean, we hear all of these trend words like machine learning and artificial intelligence and all this stuff. What are the next steps here for LibreCAN?
Yeah, LibreCAN can definitely be extended. So there's definitely room for improvement. And there's in the paper, I think on the last page or page before the last page, there's a section where I talk about possible improvement and possible next steps that can be done. So right now, we do not plan to improve LibreCAN as itself. But we actually are using LibreCAN as some sort of attack tool for some CAN security project that I can't talk at this point since we're under submission. But we found out that modifying LibreCAN a little bit for defensive security work is also a way. So that's very interesting. But as of improving the performance of LibreCAN, definitely possible, especially if you throw in machine learning and all that stuff. I am not a huge fan of machine learning because and I mean it's not a bad thing, but I think most people use it as a buzzword.
Mm-hmm.
And it's just cool. And not everything is, I mean, you can also do things without using machine learning. I mean, that's what we did here literally. But if you want to consider linear regression as machine learning, which it technically is, well, we use some machine learning here. But I'm pretty sure you can use some deep learning stuff in order to improve parts of it. I mean, everyone is welcome to keep on working on this and improving it. There's actually a lot of papers that came out this year. So this paper was published pretty much a year ago at CCS, and in the previous year, there's like I think 9 or 10 works actually that took this and built on top of it and made some incremental changes. So the paper is out there. Again, I refer everyone to my website, publications. You can read it, and I can't share the code because of IP. But by reading the paper, maybe you're able to re-implement it and improve it. That's definitely possible.
Mm-hmm. All right. Well, we don't have any more questions. It seems like everybody's very happy with the presentation and the answers. So thank you very much, Mert. Before we close for tonight, would you like to give any closing remarks?
Yeah, sure. By the way, no questions can mean that everyone is happy, everyone's satisfied, as you said. But it's also possible that everyone is super confused at this point that they can't ask any questions. I hope the latter is not the case here. But in any case, if you think about other questions or if you want to ask me something later in private, feel free to reach out to me under my email that is on this slide. Yeah, my closing remarks are I'm really thankful to ASRG and especially the host, John, today, that you guys gave me the opportunity to present my work here to a broader audience. And I'm really happy to be part of this community and develop cool tools and work on new ideas and also interact with the community, because our community itself is not that big. Although ASRG has, I think, between 3,000 and 4,000 members, it's a very small community compared to other areas. And I think the idea of ASRG, and especially this format, is very valuable, and I'm really grateful for it. Yes, so and I hope to come back next year sometime with another presentation on some defensive security solutions for CAN bus.
That would be really great. Mert, so thank you very much for the nice comments. We loved having you here today. Please come back. We love seeing good research, and especially in the area of security and automotive. And like you said, I think it's really important to have communities like ASRG. We need to challenge the OEMs, the suppliers, make sure that they're implementing the quality and security that's needed for the products to be really in the field. And it's our duty as a community, as the users, the customers, to make sure that this is kept. So looking forward to the next presentation, Mert. Thank you very much.
Thank you.
And for everybody yes, sir.
One last thing, sorry. So I urge everyone who is interested in Detroit, maybe you have an academic, maybe you're an academic researcher and want to use it, or you're an industrial you're a startup who does not have access to DBC files and want to just collect some meaningful data for their application. I'm really happy to get in touch with you if you're interested in using Detroit. So here's a link to get in touch with me, the bit.ly link. Please do that if you're interested in. I'm really happy to also see how people actually use the technologies that we develop at the University of Michigan, because we spend a lot of time for this, and we also would be very happy if you actually see that real world people actually find using those tools.
Yeah, seeing
Thanks, John.
research turn into application, right? So,
that's what we're here for, yep.
That's right. All right, guys. Well, thank you everyone for joining. We have next week a very nice webinar as well. Come join us for protecting the entire vehicle supply chain with APMAIC, securing the complete mobility ecosystem. Colin and AJ Khan will be joining us. So it'll be next week, Thursday at the same time, every time, ASRG World. So thank you once again, and we will see you next week.